sometimes, which I do. Is this going to change to being my face up here anytime soon? Because usually I wait for that. All right, we got some thumbs up. It's nothing like watching yourself talk. Great. OK, cool. Here's what we're going to do today. Mostly we're talking about we're talking about measuring things. How do we measure things in graphics hardware? And so we're going to talk about what to measure, how to measure, why to measure, these sort of things. And so at the very end, I'll talk about assignment 2, which is 3 weeks. You've got 3 weeks to do it. But we'll be spending most of our time in this stuff. OK, so we want to analyze graphics performance. And analyzing performance is really important. And those of you that write code and build systems know that a really important part of doing that is not just building the system, but analyzing how good the system is. And so we're going to talk about how to do that from the point of view of a graphics system. So why are we interested in doing this? Well, one reason is we want to understand what the applications are that we're interested in running. So to say, well, these applications are really spending a lot of effort doing this, we better make this really fast. Or we're spending all this effort making this thing fast, but nobody actually uses it. So let's characterize what we're actually interested in running. To understand how we do under the workloads. So this lets us figure out what we want to make fast, and this lets us figure out if what we've tried to make fast is actually fast. And then we want to take those lessons and use them to generate new systems. So, OK, well, this system, it turns out it's really kind of slow at this and this and this. This is something we need to improve going forward. OK, so we'll be talking about, this is sort of the broad motivation for what we're talking about today. So the first thing we're going to talk about is tracing. So this is kind of cool. So we have an application up here. It's some sort of piece of software. And then we've got a piece of hardware down here. And the question is, how does the software talk to the hardware? How does the software talk to the hardware? So this is done through a bunch of operating system magic. And so this is sort of the Windows version of the world, that it's done through what we call a DLL, a dynamically linked library. These are .a's or .libs on other kinds of architectures. And this contains sort of OpenGL or DirectX kind of system code. And it also contains what we call the driver. And so the driver in these machines is really very, very important. So you think about, well, what's Nvidia really good at? What's AMD really good at? Well, what these companies are really good at is not only building GPUs, but building the software that controls GPUs. So let me give you a crazy example of the sort of things they do here. So if you go buy an x86 kind of processor, right? Intel has spent a long time building this processor. Generally, it's going to have some bugs in it, but not very many bugs, and they're going to be really, really, really esoteric kind of bugs. It's rare that you buy a processor that actually has a significant bug in it that's something that you're going to be able to detect. Intel will tell you in enormous detail what all the bugs they find are. Okay? And when I say esoteric, I mean they're really, really strange bugs. They're really vague. GPUs, on the other hand, okay, so the typical CPU life cycle is, 5 years or so. It's a long time. They spend an enormous amount of time getting it right. GPU vendors are playing much more fast and loose with this. Their time cycles are much shorter, and they're willing to tolerate a lot more bugs on the hardware. And the reason they target a lot more bugs on the hardware is that you, as the programmer, do not program directly to this hardware. Okay? You can't, none of you have the capability, none of us have the capability of loading a program directly onto an Nvidia or an AMD GPU. Okay? You can't do it. You can't write object code and say run. Instead, everything you do ends up going through some sort of driver. And one big role of these drivers is to fix these hardware bugs. Okay? So if you actually looked inside these drivers, they have these giant case statements that say, if the hardware is stepping 1 of model 6 of the year 2009, then implement this one particular fix that fixes the errors that were in that silicon. Okay? Which sounds crazy. Okay? Seeing some nods back there. It definitely seems really crazy. But this is the sort of thing they use the driver for. It insulates the hardware. We don't talk to the hardware directly. Instead, maybe we can fix some things up in here. Okay. So what does this hardware actually look like? So what this, in normal operation without any of these bug fix kind of stuff, what it looks like is a big table. Okay? And it's a table of functions that you want to call. And so you have, GL begin and GL vertex and GL text chord and so on, all these different functions. And so it's a big jump table where every function has an address, and then you jump to that particular address, and then you run a bunch of code, and then you come back. So at its core, that's what this really does. It also does a lot of other things like compiling your programs and things like that. But when it's actually running OpenGL or DirectX code, that's what this thing actually does. So what we can do is we can go put in our own GL library. Okay, so one thing that's actually available to you in the software resources if you want is to use this trace library, which is very old at this point, but my colleague at Stanford, Kakoa, wrote this. And so you've got this big jump table. What he did was created his own library, and what that library did was just redirected all those calls. Okay, so he made it call his own call. And so maybe it goes and calls its own call and then calls the regular system call, but he can do other stuff in that. Okay, so any of you can do this. Any of you can build your own OpenGL library and make it do whatever you want. And it turns out that's really handy for a number of reasons. Okay, so what he was interested in doing was capturing a trace. So just watching all the OpenGL commands stream by, he just wanted to make a big list of them. What's actually being called? Okay, so this comes up with some interesting intellectual property kinds of things. If I can do this, then isn't it true that I can go in and look at my latest World of Warcraft game and download, I see a big vertex buffer of geometry, okay, and download exactly the shape and all the textures of all the monsters in the game? Could I do that? Okay, yeah, I could. Right? If you can do this sort of thing, you can watch everything that goes by, and you can know exactly how they do their game. Right? You can look at all the techniques they use to be fast. Okay, so this is a little bit troubling for game manufacturers. But for those of us that do research, it's really kind of cool. So anyway, possible project idea. Maybe people are interested in looking at trace kinds of things. One thing I haven't seen is really good trace utilities that deal with programmable aspects. Okay, one thing I'd love to be able to know is, what do modern games look like as far as, how do they actually use fragment shaders and vertex shaders and other programmable features? What do those actually look like? So we did have a couple students a few years ago that did this on one particular game. They sort of slurped out all the programs, and then, so you're asking is an interesting project. That was a really cool project. So they were able to come back and say, well, this is the way Quake was how they did it. Like Quake 4 was all written in OpenGL. We took out the instruction stream and we picked out what we felt were the interesting parts and then reported back on that. And what did that teach us about the hardware? So that was pretty cool. Okay, so let's say you wanted to put something in here. Why are some reasons that you would want to replace this library with something that you wanted to do? Okay, why would you, besides capturing a trace, what other things might be cool? What can you do to the instruction stream?
You might want to run on different hardware.
Okay, so be a little more specific here.
Right, so
Use the mic that's way far away. You might want to let it run on different hardware.
you might want to let it run on different hardware. So instead of that hardware box being a single GPU, that hardware box might be a cluster of GPUs.
Okay, so what I want to do is I have written a program for one GPU, okay, but I have a whole cluster out there. Well, it doesn't. What I want to do is take those calls and maybe divide them up into different pieces of the cluster. Okay? Well, that's what I can do here. I can intercept those calls, make some decisions. Oh, it turns out that, okay, well, this is in this piece of screen space, so I need to send it over here. There's different things you can do. Have you actually done this?
Yes, I have.
Okay. So what did you learn from that? Can you give sort of a recap of how that project worked?
So there's several projects that use Chromium for doing command distribution with a tile sort to tile projector array. Also did a project looking at sort first parallel memory stuff, and one thing that was very interesting was looking at measuring the amount of texture retransmission across the bus to the other computers, so I could see, where I was duplicating texture transmissions, and I could optimize a lot of stuff that way. Okay,
so we saw a couple things there. One of the things was, okay, we have 4 GPUs and they have different pieces of the screen. So we calculate where the objects are going to end up and send them to the right GPU. So that's one thing you can do with this open source software called Chromium. Okay. Second thing is looking at your command stream to, I don't want to say debug, but at least do some performance optimization. Okay, where are we actually doing more texture transfers than maybe we need to? Okay, what other cool things can we do here?
You can intercept the commands and modify them, see what it does.
Okay, so why would you want to do that?
Like if you wanted to put yourself in the Quake game, you could look for all the character commands and replace them with commands that would describe yourself, and that would essentially, I guess, put you in the game.
Okay, so you have another model that you want to render instead of the guy that's there, or make the enemy look like your worst enemy. Okay, so modify, yes, absolutely. One of the interesting things people have done with Quake, and this is why they have a lot of the anti-cheating utilities, is it's very useful to know who's like right around the corner, right? It's useful to know if I go out that door, is there somebody down there with a rocket launcher that's going to blow me away? One thing I could do is I could replace the drawing of all the polygons with transparent polygons so that I can see the guy camping around the corner. Okay? So when you're running the sort of, when you're running the system utilities, for online games, what they do is they look at your versions. They look at your OpenGL version, they look at your DirectX driver version, they look at your executable to make sure that you haven't modified those. And this is the reason why, because if they didn't look at this driver, then you would be able to replace this driver with something else and be able to modify it to give yourself an unfair advantage. Okay, let's see. So this was some of the cool stuff that, okay, let's say you wanted to print what you were doing. Okay, maybe you have a filter in there that takes every GL call and turns it into PostScript. Okay, then you got something you can print, which is kind of cool. This particular picture here, Alex Moore's now at Pixar. Michael Gleicher's a professor at Wisconsin, so that was his advisor. He was able to take this picture up here, which is sort of photorealistic, and do different rendering commands on it to make it look more artistically. Okay, so that was a really cool project, and a fun one if anybody wanted to take it on. Debugging. So the stuff that Wes was talking about here. So either debugging the application or debugging the hardware. Network transparent graphics. All right. So it turns out I got a really crummy GPU here. Okay. But down the hall there's this awesome GPU, and I can render it all over there. So what the GL library does is it takes all my commands, sends it over there instead. So all it does is it turns a stream of commands that were going to my GPU into something that are going to go into the network. That would be groovy. I want to do stereo. Okay, so what that's going to require is that I render from both my eyes. Okay, so maybe the original rendering is from right here. What I do is I split it into two rendering streams, and I slightly perturb the transformation matrices so they look like they're coming from both my eyes. So my understanding is Nvidia sells, I don't know if it's software or whatever. Okay, what I saw at Envision this summer is they gave out everybody 3D glasses at the product launch. And they took Age of Empires 3 or whatever it's up to, and they were able to show it. And what their software does is it takes a single stream, single view input and does the left-right eye transformation and then broadcasts both of those things. And you can buy this at home. Does anybody know about this? Tell us about it.
No, I saw a demonstration at Kerner Optical in San Rafael of the same software. So it's exactly as you described.
Exactly as I described. That's great. It looked really cool. And they said, this is free, right? It's really easy for them to make that transformation if they want to. But they felt that it would be a cheap way to be able to get 3D in people's homes. And the guys I know at NVIDIA Research are very excited about this. They say it looks great for a very cheap price, which is pretty cool. Okay, so that's what they're doing. They're intercepting the command stream. They're changing it a little bit. Regression testing. So does it work the same as it used to? Okay, so you can get and store the stream and store the output and then be able to test it against your new architecture and make sure it's going to be the same. Okay, reverse engineering. You want to know what sort of GL techniques that the guys use to make Quake run really fast. Which commands are they using? How are they sequencing them? How are they able to hide geometry? Like what are they rendering and what are they not rendering? Okay, you can record all that stuff. Cheating, I talked about that, and stealing. So these are the unethical parts of what you're doing here. Okay. So these guys also wrote, they wrote something called Hijack TL. These are 4 scenes from, I think, the original Quake that they did. And they're 4 different kinds of rendering that all had the same input source. And they wrote filters that would change it into blueprint rendering or pen and ink or different styles. So, which I think is really pretty cool.
It doesn't affect the...
It doesn't affect... Use the mic.
it doesn't affect the performance. I mean,
Okay. So does this? Okay. So should this affect the performance? What do you think? Okay. So what does it make run slower then?
Because we have to check every single the OpenGL command, and so and if you change that one, maybe that affects the speed.
So it would seem likely that there's more CPU load on the program. Okay, because the CPU has to look at every command and do something with it. So if your program was bound by CPU time, then it's likely you're going to see performance slowdown. If your program is GPU bound and the bottlenecks were in the GPU, maybe you're not going to see anything. So I would agree with you, it's not free. I can't really characterize, it depends on what you do as to how expensive it's going to be. But certainly it could and should cost something. Okay, but I really like the visual output. This was pretty cool stuff. Okay, so what can we do with tracing? We can, at least what Kakao built here, he had 3 different things he could do with it. One was to play it back on hardware. Okay, so any of you that play games know that you can sort of record a trace, and then you can play that back. And usually that's built into the game engine. What he would do is he would record a trace of GL commands, and then you could just play that trace back, and it would just send them all to the graphics hardware. So that ends up being very high performance because it doesn't have any of the application getting in the way. All it does is just stream commands. Okay, he could collect statistics. Okay, so what sort of statistics might you care about? We'll talk about this a little later in the lecture, but what sort of things might be good?
Like how many triangles you're trying to put up there, and
how many
the flow
triangles
rate and stuff like that, and so you can see performance issues.
Okay, so yep.
Number of state changes.
Okay, so we've talked about OpenGL being a stateful interface, and we say, okay, let's change the state of the color or the texture, or change any of the state. Okay, and some state changes are more expensive than other state changes. And one thing you can look for is how often are you changing state. If you're looking at every other command you're changing state, it's likely that's going to be bad for your performance. So you record a trace and you look for how quickly you do that. Okay? Or you can simulate. You can say, oh, I've got this new architecture here, and now I've got a real trace of real program that people care about, and I want to run it through my new architecture, and let's see how it's going to perform. Okay, so very useful to be able to capture these sort of things. Does anybody know about recent utilities that let you do this in DirectX or let you do this in OpenGL? Okay, so I think the students that did this used a program called GL Intercept to sort of slurp it all down. I don't know about any DirectX ones, but I'm sure if people Google, you're going to find stuff. So from a game point of view, it's much more interesting to have a DirectX trace, but I don't know DirectX, so I haven't played with that myself. Okay, so you look at a system, and we're trying to figure out why it's running slow. So I've sort of got 2 slides here. The first one is to talk about places where in the system that might be limiting our performance. Okay, what I'm going to show in the second one, the next set of slides, is how we might go about diagnosing that. How do we figure out which one of these? But first I'm going to describe what the bottlenecks might be. Okay? So we're going to start sort of at the application level and then move through the graphics pipeline and talk about where we might have bottlenecks. So one of our big goals is to figure out where these bottlenecks are. Okay? If we figure out where our bottleneck is, then maybe we can rewrite the program to eliminate that bottleneck and make things run faster. So it's important that you're able to both identify the bottlenecks where potentially they might be, and then to figure out exactly the ones that are limiting your performance. Okay, so one of the big ones here is CPU. Okay, so we're spending a lot of time in our application. If we're doing real-time graphics, it's usually associated with some sort of simulation. Okay, and then we want to render the results of that. Well, the application part is all going to run on the CPU, and that might be limiting our performance. It might be that it's spending all of its time doing this, and it just can't send graphics commands to the GPU fast enough. Okay, it just the GPU is faster than the CPU is. This is more and more common today. Okay, and many, if not most, games today are limited by CPU speed, and so it's a big challenge for graphics people like Nvidia or AMD to try to mitigate this bottleneck because the GPUs are getting faster more quickly than the CPUs are getting faster. And CPU code is not multi-core aware often. So this makes things kind of tough. And so this is why we see people trying to move other stuff onto the GPU. Okay, so you might have seen some GPU-based physics stuff. Okay, probably the next big thing is to see GPU-based AI, doing artificial intelligence. These are tasks that are very expensive currently on CPUs. So they say, boy, maybe if we move some of those tasks onto the GPU, then it's we're going to have less work to do on the CPU, and we can continue to get faster. Okay, so that's one of the first places you want to look. Okay, then we take all the commands we want to do and we send them over to the GPU, and we send them over a bus. This bus is fairly slow given the rest of the system. So PCI Express will maximum send, I believe it's up to 4 gigabytes each direction per second. Okay, so it can send 4 gigabytes a second. Now, we're talking about a memory system here that's probably max about 20 gigabytes a second. And we can get memory systems on the GPU side that are over 100 gigabytes a second. So this is a pretty narrow pipe that we're sending data through. Okay? So it's only 4 gigabytes a second. And it might be that we just have so much data to send across, this guy can keep up and this guy can keep up, but this little narrow pipe is limiting our performance. So, yeah.
Wondering, when you said 20 gigabytes per second, that seemed like a lot. Because, I mean, the game itself is maybe like a half a gigabyte. So why would you need to transfer that much information over?
Okay, so, right. So first, that's a not to be exceeded value. So that only works if you have really big things. If you're sending a lot of little small things, it's going to be much, much less. Okay? Let's say you're doing a game with textures that change every frame. Okay? So every time you have to send, another 100 megabytes of textures every single frame. And you want this game to be able to run at 100 frames a second. Okay? Well, that's you're already way over your budget, right? 100 megabytes times 100 frames a second is 10 gigabytes. So you're already over. Right? So generally in the compute world, you see this when you have lots of things to send over, not very much compute, and lots of things to send back. You're usually going to be limited by bus performance because you're going to be spending all your time waiting for that to happen. When you have rapidly changing geometry, okay, like this big, hundreds of millions of triangles, and it's different every single frame, and you have to send that across, then that's something that's often going to limit you too. So basically what ends up happening is people structure their applications so they're not sending this big wad of stuff across every frame. You try to use display lists. You try to use geometry that doesn't change every frame, so you can leave it over on the GPU and you don't have to send it over and over and over again. Okay. Then we get over here. We start, so we load all our geometry here into video memory, and we start running here. Okay, so one of the first things we have to do is transform our vertices. Okay, as this has gone on, this is our vertex programs here. Okay, so let's say we have lots and lots of triangles, but they're all really, really small. Okay, that's a lot of vertices that we're going to have to process for every frame because it's going to take many, many triangles to cover the screen. If we have a very complicated vertex program here, that could limit our performance. Okay. When we get to rasterization, there's a couple different big pieces of work that we need to do. Okay? There's work we have to do on every triangle, okay, no matter how big the triangle is. And then there's work we have to do on every fragment. So if we kind of look at a graph of performance versus size, actually, we're going to make this work versus size. Okay, so to rasterize one triangle, okay, there's a fixed amount of work you have to do. I'm horrible with chalk. Fixed amount of work you have to do no matter how big the triangle is. Then as the triangle gets bigger, there's more and more work you have to do. So this is an area where you're limited by setup. And this is an area where you're limited by what we call raster performance. Okay, does this make sense, this sort of graph? Okay. So if we have a whole bunch of really small triangles, we're probably going to be limited more here. If we have a bunch of really, really big triangles, it's more likely we're going to be limited here. You often see this when you're doing shadows. So when you're doing shadows, I'm not going to talk about the shadow technique, but you end up doing a lot of rasterization on a shadow pass of the graphics hardware before you actually draw stuff. So shadows are often limited by rasterization. And so what you'll see in GPUs today is they have special purpose hardware that just does shadows and makes this raster pass very, very fast. So it can do many, many shadow texels on every clock cycle. Okay, but these are two different limits that you might see within the rasterization part of the pipeline. Okay, then you get down to fragment shading. Okay, you get this really complicated fragment shader that does all these cool effects and has 300-400 operations in it. Okay, that could limit your performance. Okay, you're using a lot of texture. Okay, this is an interface that has only a finite amount of bandwidth. Roughly the ratio here between the bandwidth and the amount of compute that you have here changes every year, but it's getting bigger. So today, roughly, it's about 20 flops you can do for every word of memory bandwidth. Okay? Every year that changes, and every year that number goes up. Let me say that again. For every 20 flops you do here, okay, you can do one memory read, or one memory write. Okay? And that goes up. And so if what you do is you read a word from texture and you don't do anything with it, or you do 2 operations with it, and then you write it to the frame buffer or something, then you're probably going to be limited by this bandwidth because you got all this hardware that's sitting here with lots more power than it needs, and it's going to be waiting for this guy to finish sending memory bandwidth. Okay. And the final place here is you might be reading and writing from the frame buffer all the time. You might be doing you have lots of fragments. They're all very simple to compute, but your fill performance is what it's called. How fast can you fill up your frame buffer? How fast can you compare to the depth buffer that's in your frame buffer? You might be limited by that. Okay? So this is just saying where bottlenecks might be as we walk through the pipeline. Pretty much anything could be a bottleneck, and the question is how do we recognize what the bottlenecks are? Question, or you're just holding your...
Sorry.
Any questions on this? Yeah.
Going from here to the actual display, so there's another bottleneck there, right?
Well, the hope is that so you do have to read out the frame buffer, right?
Right.
So fortunately, the bandwidth it takes to read out the frame buffer pretty small compared to the bandwidth of the memory. It's also fixed, right? So your monitor runs at only certain modes, and you run at 1600 by 1200 at 70 frames a second. You can select that in your display panel. Okay, that amount of bandwidth just really isn't particularly large compared to the amount of bandwidth that it takes in here, generally. Okay. So, this was from, this is a slide from Simon Green. He's an engineer at Nvidia. And so he was offering this as an example of how you might figure out where your bottlenecks are. Okay, I don't want you to think this is the only way you can do it, but what it shows is some different techniques you can use to sort of tease apart all these parts and figure out which one of these parts might, cause your actual bottleneck. Okay, so what he does is he does a lot of varying things. He says, okay, run your application, get some statistics, and then change something and run it again. And when you change something, you're going to see if you have a difference in performance before. And if there is a difference, then it's likely that what you just changed is sort of the heart of what your bottleneck is. So the first thing he says is, okay, run the application, change the frame buffer bandwidth. Okay, and you can often do that in control panels. They're kind of elite hacksaw kind of control panels, but they let you change different clock rates on your GPU card. And what he's essentially saying is turn down your memory performance. Okay, so you have a clock rate of the memory on your graphics card. Turn that down so it's a little bit slower. Okay, that's going to affect more than one kind of bandwidth, but it's certainly going to affect your frame buffer bandwidth. And then see if you're limited by your frames per second. Okay? And if you are limited by that, okay, it's entirely possible that you're going to be limited by frame buffer bandwidth. Okay, so let's say it doesn't change. Then what you change is the sizes of your textures or the complexity of your texture filtering. We haven't really talked about texture filtering yet, but just think about, what's a texture? It's a big picture. So what we're going to do is we're going to take our textures and we're just going to make them very small, very simple pictures, smaller pictures. And what the filtering says is how many samples do we take from a texture to be able to get the final value of the texture at a particular fragment. Well, it turns out that the more samples you take, the better it's going to look. And so maybe what you want to do is say, okay, we're going to dial that down a little bit. We're going to make the textures look worse. We're going to use a simpler texture mode. We're going to sample less and be able to get roughly the same visual output. And maybe it's not going to look quite as good. But what that's going to let us tell is, is that going to change the frames per second? Okay? So if we dial down our textures, we use less texture bandwidth, and it changes the frames per second, hey, maybe that's going to show us that the issue there is texture bandwidth. Okay? So then we say, okay, neither one of these things changes. All right? So now what we're going to do is we're going to vary the resolution. We were running at 1600 by 1200. Okay? Now we're going to turn it down to 640 by 480. Okay? So in our pipeline, what's going to change there when we do this?
A lot less fragments floating around.
Okay. Will we change the amount of vertex work?
No.
Okay. So we're not going to change the amount of vertex work, right? All the same triangles are going to go into the pipeline, but now it's a smaller screen, so we're going to generate less.
But doesn't that also change the frame buffer bandwidth?
It would also go, but in this particular chart, we already decided that it wasn't the frame buffer. Okay, good question. It could, but it won't. We've already made that determination here. Okay, so we're saying, okay, dial down the resolution. Now we're sort of going to isolate the parts of the system that have to do with fragments and pixels. Okay, so, but there's more than one thing it could still be. Okay, so what could it be? There's a couple things we talked about when we looked at the bottlenecks. What could it be if we vary the resolution and the frames per second varies? Okay, where could the bottlenecks be?
Raster operations.
Okay, one of them is raster operations, and what's the other one? Raster, and what's the other one?
Fragment shader.
The fragment shader, right? These are the two things that have to do with the amount of work we do on every fragment. All right, so this one has to do with how complex the fragment program is. This one does not have to do with anything with the fragment program. Okay, so what we're going to do is we're going to vary the complexity of the fragment program. Okay, so we're going to have a less complex fragment program. Okay, it was doing all these amazing visual effects. Now we're dialing it down. It does something very simple. And if that changes the frames per second, well, it's likely we're going to be limited by fragments performance, by the performance of the fragment program. If it doesn't change as a result of that, it might be the rasterizer. Okay, so we do all these things. Nothing changes. Now what we go do is we change the vertex program. Okay, we're moving sort of backwards up the pipeline here. And we say, all right, we're going to vary the complexity of the vertex program. We used to have this big complicated thing. Now it's something really simple. Okay, so does that vary it? Okay, well, if it does, then perhaps we're limited by the vertex transform. Okay, so then, okay, that doesn't do it either. All right, so now we can look and say, now we're going to change one of a couple things. One is we're going to change the size of the vertices. So maybe we specified all of our vertices as floating point numbers, and it sends those across the bus. We say, all right, now we're going to change those to doubles. They're going to be twice as big. Other than that, nothing changes, but we're going to change those to doubles. All right? Then that's going to be something that measures how fast our bus is, because what it's really going to affect is that rate across the bus. Or we can say, use some sort of hacker utility to change the clock speed of our PCI Express bus. Okay? Either one of those things is going to take a look at the bus. And if it turns out that none of those changes, then possibly it's going to be CPU limited. And you might be able to test that by changing the clock rate of your CPU, because I know there's utilities that will let you do that too. Although it's a lot harder today than it used to be, right? Like Intel really doesn't like it when you change the clock speed of their processors.
Yeah, they make you pay extra for the ones that you can vary it.
So my understanding is the issue that they have is that they will build a processor at 2 gigahertz, and then people will buy these processors and then try to resell them at 2.5 gigahertz, and then when it goes wrong, they blame Intel. Okay, kind of bad news for Intel. So now Intel sort of locks down the clock speed of its processors so that it's harder to change. AMD, on the other hand, welcomes people doing that. So that's just a corporate decision they've made. They're much more comfortable with you being able to change the clock speed of their processor. Okay, so that might be a good place to start. You could think about doing this whole diagram upside down and say, okay, we'll start here and we're going to change the speed of our CPU and so on. Okay, but this gives us an idea of how to, our program's running too slow. What do we do? Here's some ideas for where you can identify what's really gone wrong there. Okay, now there's tools that help you do this too. So Nvidia has this really cool set of tools, and this is actually last year's diagrams, but this is something that they'll give to developers for free, and it gives you this enormous amount of detail of what's happening in the GPU. So it's called NV-PerfHUD. It's the performance heads-up display. The drivers support it natively, and so you can look at sort of time goes across here and look at graphs of sort of how busy each of the units are. Okay, it gives you, let's see, this is showing how many calls it's doing and how long it's taking, and I can't even read this because it's way too blurred out, but it's going to give you all these, these are draw calls, I guess. It will also let you run your simulation here and do graphs on top of your simulation, which is really useful. So you're watching it run, and it gets to this part of the game that's really, really slow for some reason. You can watch it draw all these graphs on top of your game or your simulation or whatever you're running. So it's really handy to watch and see what changes. So I haven't used this myself. I'm really happy to get feedback from people that have. But Nvidia and AMD and Intel are very interested in seeing people use their graphics hardware to the best of their ability. So they're really nice about giving you these sort of tools to see, where your performance gaps are. Okay. Okay. So any questions on sort of measuring stuff?
So when you use a tool like this, how do you isolate the drawing time for this tool from your actual program? Like, what if your program is actually pretty fast, but once you load this tool on it becomes very slow? So if that was true, then it wouldn't be a very useful tool. And it's probably fair to say that it's in NVIDIA's best interest to make this as non-obtrusive as possible. So there's a couple things that help. One is that they control the driver. So it's pretty simple for them to layer. I mean, frankly, this stuff is really simple. There's not very much graphics complexity in here. It's pretty easy for them to be able to do it. The second thing is that they have access to what are called the performance counters inside the GPUs themselves. So in processors, CPUs, GPUs, they have all these little counters that keep track of stuff. And they use it for optimization and data and so on. And they're free because they're already built in. And NVIDIA can get to those counters and get this data very easily without very much compute time. So you mean most of this is built into hardware? So like the things that they look up?
At least some of it is built into hardware. They're very, Intel will tell you all about their performance counters and their CPUs. You know exactly what's there. NVIDIA and AMD don't really tell you about the performance counters in their GPUs. So historically, CPU vendors have been much more open with their architectures and how they work internally than GPU vendors have been.
You do have to. Well, I know Intel does factor in the overhead for running an application like this, though. It's almost negligible, but not quite.
Okay, so that's a very nice set of adjectives there. It's their goal to make it negligible. If it's almost negligible, it's probably pretty good. If it was significant, then it wouldn't be a very useful tool.
I'm not quite sure about this, but so if you're overlaying on top of your game or whatnot, doesn't that mean that your rasterizer has to do less work because the stuff that's overlaid is very simple and the stuff behind it doesn't have to process?
So you could think of them doing it a couple. I wouldn't write it in that way if I was NVIDIA. I would write it in a way such that the last thing that I drew, I would draw everything just totally normally, and then the last thing I did was just slap that up there. And in fact, the hardware often has support for that. That's how your mouse works. right? So it draws the whole frame, and then it draws your mouse. There's actually special hardware that just deals with overlays, they're called, for your mouse. And so my guess is they implement it that way because it would not give you realistic results if it culled out everything that was behind the graph. Okay, so I'm interested to hear people's feedback with this sort of tool. I have not used this myself, so if people use it along the way, please let me know how it goes. Okay, so applications and scenes. So now we're going to look at different kinds of applications and scenes and benchmarks and sort of what we can learn from those. I'm going to skip some of this stuff. Okay, so the first thing we're going to talk about is benchmarks. So what's a benchmark and why do we use a benchmark? Okay, what do we mean when we say benchmark? Go. You raised your hand at the wrong time.
A benchmark is a way to measure the performance of a machine given a test of some sort.
Okay, so the important part there is the test of some sort.
Yeah,
right?
So you have a lot of options on that, for example. I mean, and a lot of controversy. You know, like for example, on CPUs, the Spark is very managed very... Spec, I guess it's called spec, is managed very, is controlled very much so that the benchmarks try to give the best performance analysis for the chips. So similarly, you have a lot of options on what your benchmark is and how you can run those tests.
Okay, so what I'm hearing is a benchmark is a test, okay, and you can run the test on your machine and get some sort of measure of performance out of that. Okay, so what makes for a good benchmark? What are some of the characteristics we want if we're choosing a benchmark to measure a graphics system?
That the benchmark accurately represents the workload that you're trying to estimate for a particular device.
Okay, so the benchmark matters. Okay, you can choose any programs to run, but you'd like to choose programs that measure the same sort of thing that you care about. Okay? If what you care about is playing video games, then you're not going to care about benchmarks that are interesting for people that are doing industrial design with CAD software. Okay? If you're doing visualization, you want benchmarks that are going to have the same characteristics. So you want something that's meaningful in your context. Okay? What else? What are other characteristics of benchmarks that you care about?
Well, so for acceptance and use within the community, you want it to be pretty simple and lightweight in the sense of, it's not a big, huge distribution or something. Yeah.
Okay, so you want to pick benchmarks that are easily used by the community that can have widespread acceptance. Okay, because you want everybody to use your benchmark, right? You want everybody to go against this. So to some extent, you'd like things that are multi-platform. Okay, you'd like things that run on lots of different kinds of hardware. That would be good.
You wouldn't want your benchmark to be biased towards one GPU.
Okay, so this is really important. If you care about performance and you care about comparing, then maybe you're not going to want Nvidia to write all your benchmarks. If you're AMD, you probably don't want Nvidia to write all your benchmarks. Okay, so, and it's very easy for those companies to write things that are particularly oriented to their own hardware. We will see this when Intel's Larrabee comes out, because when Larrabee comes out, it's going to be good at very different kinds of graphics than traditional GPUs are. And we will see Intel promoting its performance on things that it's good at. And you will see NVIDIA and AMD promoting their performance on things that they're good at. And they'll each be arguing with you and saying, the things that really matter are my things. Ignore the other guy. Okay, so bias is a really important thing. You want things you can't cheat on. Okay? And that turns out to be really important. And in graphics benchmarks, it comes up. I have an example in a second. But where the vendor says, well, we're not going to really do it the way that they expect us to do it. Instead, we're going to do this cheating thing. And it turns out we can do it in a much more efficient way and get a better score. Okay? The other thing you really want is you want something that's meaningful. You want something to come out of the benchmark, and you want a measurement. And you want a measurement that actually means something. So usually, when I read, Hot3D or whatever the Ars Technica or whatever the good reviews are, they go out and measure frames per second. Okay, if you will go buy a new graphics card, they say, okay, this graphics card is going to run Call of Duty at this frame rate for this configuration. Okay? That's something that matters to you as a customer. That's what you care about. How fast does it run this? Okay? So that's a meaningful measurement. You would like your benchmark to come up with something meaningful. Okay. So this is an old benchmark. This is a different spec benchmark. So spec is the systems performance, something cooperative, and they come up with all sorts of benchmarks. And the one they're really known for is the CPU benchmarks. They have a set of benchmarks that are for OpenGL. These are very old. So I don't suggest that this is a new set of benchmarks, but they talk about sort of how they came up with these benchmarks. So one thing they use is they use real applications that people cared about. They got submissions of applications from companies that cared about stuff. So Alias Wavefront does Maya, which is a modeling kind of software. Okay, IBM. Data visualization kinds of things. So they got applications people cared about, and they used these. And they talked about sort of what they cared about. You know, they wanted real data sets. They wanted real models that people, you know, might actually care about. Its results were actually based in frames per second. Okay, so these are sort of, I mean, they wrote a whole paper on this is how we chose the ones that they did. They also talked about, and this was kind of the interesting things, we didn't look at these things. Okay, we don't have, these are things that don't matter. Okay, we didn't test these in our benchmarks. Okay, what happens if you have different kinds of primitives? So we say GL begin, GL triangles, and then do a bunch of triangles. What they don't have is like GL triangles, GL quad, GL triangle strip. They didn't do experiments like that. They only had one type. Okay, input effects on the event loop. If you're clicking all over the place, moving your mouse all the time, that might affect your performance. They don't test that. Okay. User interface stuff. You're running this awesome, cool GNOME desktop on Linux that takes all that, you know, didn't look at that. They don't have lots of models interacting with each other. They don't look at CPU load. This is not important at all. They don't look at having, you know, what happens if you're running like this with two windows on top of each other. They just don't look at some of these things. So they're very careful about saying what they don't look at. And I think that was valuable as well. So in the gaming world, they take these benchmarks really, really seriously. So this is kind of an old article, but what they talked about was that this 3D mark is, I guess, one of the common things for people that care about games. Every year there's a new 3D mark. It's a set of benchmarks that are used for games to evaluate new graphics cards. I get the impression people care about this a lot. And they argue a lot about the numbers every year. Like, is this, you know, is this biased toward this, biased toward this? Is this really meaningful, and so on. So Nvidia decided here that they're distancing themselves from 3D Mark 2003 and believes that this benchmark test has no relation to reality. So I had some quotes here. They said that the CPU performance doesn't play a big role. Only the graphics card is responsible for the 3D Mark score. That was a criticism. It seems to me that's kind of a good thing. The test used Pixel Shader 1.4 for all the pixel shaders. It turns out they don't use anything from Pixel Shader 1.3, which is what they really cared about. One of the quotes was that the tests have a Doom-like look, but use a bizarre rendering method that is far from Doom 3 or any other known game application. This method makes for an interesting demo, but is so inefficient that no game would ever employ it. Okay, so they felt that the 3D Mark people had written a benchmark that was not indicative of the way that people wrote real games. Okay, and that's a totally legitimate comment. That's an important comment. Like, you want benchmarks that reflect what people are actually doing. So these are, but they take the scores very, very seriously on this. So here's a question. Let's say you're Nvidia, okay, and you see this 3D Mark benchmark, and you know that it's really important to your company. Is it legitimate for you to release a driver that is optimized for 3D Mark? Is that okay or not?
Well, what do you mean by okay?
Well, from, I guess, the point of view of an academic, okay, so we're unbiased observers here. Is it fair for them to be able to do that and say, our 3D Mark score is 100, whereas with the unmodified driver, their 3D Mark score is 80?
Well, if I can get the driver that they use to get that score, then I think it would be fine.
Okay. And that's, okay, so that's, so one of the big things in CPU benchmarks was dealing with one thing they required is you've got all these CPU benchmarks, and they require that you use the same compiler settings on all of them now. It used to be you'd have different compilers for each one, and they would give you the best result. And they said, well, that's not really meaningful. You need the same settings for everything. So I think it is important that the driver be available.
But it's also dependent on the application, right? Like, let's say there's a graphics program that, let's say there's a graphics program that's targeted for like taking sonograms or something, where a surgeon wants to see the crack in a bone or something.
Okay.
Right? And he's particularly interested in how sharp the images are, what detail is presented. It may not have any impact on how your games are going to look like.
Right. So
there may be different benchmarks for
accuracy versus performance.
Right. If it's a motion picture,
right,
maybe it's a different thing.
So it's fair to say that this is a sort of benchmark where they really are just looking at performance. Okay.
Yeah, but if Nvidia tries to sell their cars based on this benchmark, and then says, oh, we have the score of 100, but in reality, when you play the games, it's actually with the drivers of 80, then you're actually kind of misdirecting the customers.
So, and this is what this is why it's fun, because if you go on boards, the two companies or their supporters just slag each other all the time. Oh, they're cheating on this benchmark. They've released a special driver that only works on this. So what happens in practice is they definitely look at this when they're building their drivers. The hope is that the techniques they use to make this run fast are ones that are applicable to other games. But the fact is there's maybe 10 or 20 or 30 games that NVIDIA really cares about. And so in their drivers, they have special things just for those games, okay, where they look for this particular pixel shader that's expressed in exactly this way, and they've already compiled it to what they know is the best way, and they put that out. Their compiler has these incredible special cases. And I would argue that's probably okay, because that is so much of what people want out of it. I mean, they want something that's going to be really good on this game, and NVIDIA's giving them that. Comment?
Okay, so this is a technical class, but we're talking about an ethical issue, but I can't let this slip by.
Okay.
Okay, so the point that was made is that NVIDIA releases a special driver that scores really well on this artificial benchmark, but still game performance sucks, right?
Okay.
And so the assertion is that they're cheating their customers, and I understand that point. The counterpoint that I want to make is that the benchmark sucks. And it's not necessarily NVIDIA's fault that their good score arguably cheats their customers out of more frames per second on a game, because the target was the benchmark that they were worried about, as opposed to actual frames per second out of the game, which is what they should have been focusing on to begin with.
Well, and that's the point they're making here. They're saying, look, you gave us this bogus test. We're going to figure out how to run well on this bogus test. We think it's bogus, but we're going to look really good. And the quote they had was, designing hardware around the approach used in 3D Mark 2003 would be like designing a 6-lane on-ramp to a freeway in the freak case that someone might drive an earth mover onto it. It's a great quote. Yeah, I mean, I don't think there's a right answer to this. In practice, the vendors definitely look at this and optimize for this, and to some extent. You can decide for yourself if that's okay. What I want to make sure you know is that people do this. And regardless whether you think it's ethical or not, it's happening. And it would be great if the effort they were putting into this also helped all other games.
I was just going to say, I don't know if the ethical implications of cheating on one of these benchmarks is great enough that one of these vendors is not going to optimize for these benchmarks as much as they can, because these numbers have serious implications for their stock price.
Yes. So, and the question is how much cheating is good cheating. So one of the other articles I read had an assertion, again against NVIDIA here, was that they felt they were actually cheating in the benchmark they were doing. So it was something in Half-Life where I guess the guy gets in like a mine car or something, and he's like going along a track, and it's like a pre-done movement. And so what they found was that if they took the positions and they moved them a little bit away, then it had these totally huge impact on the rendering performance, or what you saw, such that it was obviously incorrect. And they'd put something in the driver such that it was optimized for this path only. And I would argue that's probably that's wrong. That was an incorrect thing to do. And I don't know enough about the details, but I think it's important that you're You can optimize for this, but at least it has to do all the work that it's promising that it's doing. You can't cheat. Okay, so we're sort of dropping down a level now, and we're looking and saying, come on. We're looking and saying, okay, when we look at scenes, what do we actually care about measuring here? Okay, so we have this great trace program. We can get all sorts of statistics. What are the things that we care about? Okay, and we want to measure these things in our traces. So what kind of primitives are we rendering here? What is the depth complexity? And this is actually really important. We render maybe many fragments for every pixel. Okay, well, it's a waste of time to be able to render things that we're never going to see. So you'd like your application to be really good at keeping the depth complexity down. And I have this slide later on, but the analog here is Disney. What people at Disney say is that when you go to Disneyland, anything you can touch is real. And anything you can't touch is fake. And they're very careful about spending all their time building things that are very close to you, and then they fake everything else because it doesn't matter to you. So if you go like Pirates of the Caribbean, they have this old kind of stone here. It's real stone up to here, and it's like paper mache above that. So if you're designing a movie, if you're Pixar, then you try to keep this depth complexity as low as you can so that you're only rendering the things that you care about. And anything that's outside of the view frustum, you don't model, you don't render, you don't do anything with that at all. So good applications will keep this depth complexity low. You'd like to know when you're tracing these games, how good are they at reducing depth complexity? Okay, are we using immediate mode or retain mode? How big are our triangles? How much do our triangles vary? Okay, it's very different if we have all triangles of 10 pixels versus a bunch at 1 and a bunch at 1,000, even if they have the same average. How good are we at culling and clipping? Are we rendering lots of things that we never end up seeing or not? Okay, how do we shade? Okay, so we can look at statistics here, and we can be able to make some conclusions about the strategy used to render here. So this is a cyberware scan of somebody's head. And if we trace it, we figure this stuff out. So we do this many vertices, this many triangles. This is how many fragments come out. This is how big the image is. And those are all the GL calls we made. Okay, so then I can ask you some questions about this. All right? How many frames did we render in this benchmark? 240. Why do we say 240?
It's on top.
Oh, yeah, good point. Okay, so besides that, okay, ignoring the 240 frames on top, how do we know how many we measured, we rendered?
The GL swap buffers?
Okay, we could look here and say, okay, we swap buffers 240 times from front to back. There's 240 frames. Thank you. That was really good on the 240 frames. Okay. What information is passed per vertex?
Colors and normals.
Colors and normals. Okay, but that's all. No textures, for instance. Okay, so we know we're not using texture in this scene. All right? What kind of geometry are we using? Triangles, quads, triangle strips, quad strips, lines, so on.
Looks like disjoint triangles.
Okay, and why would you say that?
Whoop, I take that back. Some number of triangle strips.
Okay, so we think it's triangle strips, and why do we think that?
Because if it were disjoint triangles, the number of triangles would be the number of vertices divided by 3.
Okay, so we specify vertices, right? If we did disjoint triangles, if we said GL triangles, then we would say vertex 0, vertex 1, vertex 2, and that creates a triangle. Vertex 3, vertex 4, vertex 5, that makes a triangle. So we would have 3 times as many vertices as triangles. Instead, we have roughly the same number of vertices and triangles. That leads us to believe we're probably using some sort of triangle strips. Cool? How big are the triangle strips, short or long?
Looks like they're pretty long.
Okay, I would say pretty long. Why do you think that's the case?
The disparity in the number, the size of GL begin versus the number of normals and vertices we're sending down.
Okay, so roughly our strip size would be 60,000 over 452. Right, we don't have very many GL begin calls. We also know that because these two numbers are really pretty close together. If they were shorter strips, then we would see more of a disparity there. Okay, are we using any display lists here?
Yes.
Okay. And so we can look at this and see that our strategy is actually to create a display list and then call it 240 times. Okay, so we create one big display list, go. Okay. Let's see, I think that's all the questions I had on this one. Okay. Why do we have twice as many 3D triangles as 2D triangles? Okay, so particular here, we haven't talked about this in class, but there's a stage in the graphics pipeline where it's culling. So what we do is when we draw an object that's sort of 3D, it doesn't do any good to draw the back of my head, you only want to draw the front of the head. So you use this stage called culling to throw those out before they're rasterized, to throw out the ones that are facing away from the camera and keep the ones that are facing toward the camera. Right? So we've got this guy's head, it's all the way around. We appear to be throwing out roughly half the number of triangles between here and here. Okay, so there's probably some culling going on there. Okay. Cool. Try another one. This is a benchmark. Right? So it's interesting to see what's inside the benchmark. This is one called light. Okay. What kind of geometry are we rendering here in light?
Looks like we're rendering quads.
Quads. Okay. Why do we know we're rendering quads? That's correct.
The relationship between the number of triangles and the number of vertices.
Okay, we draw 4 vertices, we get 2 triangles. Okay, twice as many vertices as triangles. Okay, this is what's called a radiosity solution. All right, so what we do is offline, we compute like all the light transport in the scene and figure out what color everything is, and it's modeled as a bunch of quads, and each quad figures out what color it is, and then, I mean, this is obviously very nice lighting here. This is a good, high-quality radiosity solution. Okay. How do we know this is a radiosity solution and not something that's rendered using the GL lighting model?
There's no calls to GL light.
Okay. There's no lights. There's no normals. Okay. There's no materials. Okay. Instead, what we do is we pre-figure out what color every vertex is and then just render the whole thing. Okay. Why is there a 9-to-1 ratio between the number of 3D triangles and 2D triangles? What could be a good explanation for this? Okay, that's exactly it. All right. It turns out this scene has 2 stories, and it's very complex on the second story, and it's all being clipped out. Okay, it's outside the view frustum, and so we're only looking at the first story. Or there's some rooms behind here or something. Big scene. Good answer.
Sorry, how'd you know it was quads?
We know it's quads because of the ratio between vertices and triangles is 2-to-1. And in fact, pretty much exactly 2-to-1. Okay, and every quad will 4 vertices, 2 triangles. Okay. Okay, this is a panoramic image. It's stored as a big cylindrical environment map. Do we have big or small triangles here? Very big. And how do we know that? But many, many fragments. Okay? So the way this works is, this is like, I think this is moon, but you have this cylindrical map around you, and it's just giant triangles that make up this cylinder. And so in QuickTime, you can sort of turn all the way around and see this. And so it's just giant texture-mapped triangles. Question?
The decimal, does that mean there's clipping going on or something?
It's actually averaged over the number of frames.
Okay.
So it's average per frame. Good question, though. Okay. Here's one that's it's called Performer Town. This is a more complicated scene. So if you look at the right side there, there's just tons of. So this is like the first really. It's an old scene. It's done in an SGI environment called Performer. But it's one of the first textured scenes that was done. So this is one of the first textured benchmarks. One thing you'll see is it uses a lot more GL calls than some of the other guys. Okay, so that's a good thing you know out of a benchmark. You look at some of these other ones, they don't use very many GL calls at all, or very many different GL calls. Okay, you can see it gets down to 1s at the bottom. This thing is using GL calls all over the place. Here's Quake, which is kind of interesting. Okay, so It uses lots of different GL calls, okay, we can figure out. It actually uses two kinds of vertices, which is interesting. So we look and we see we use vertex 3FV and vertex 3F. Okay, the second and third one up there. So vertex 3F takes 3 arguments, x, y, and z. Vertex 3FV takes 1 argument that's a 3 vector. Okay, I have no idea why they chose to do that. They presumably had some good reason to do it. I mean, these guys kind of know what they're doing. We can also see that we have really big triangles here, too. Right? There's just not very many triangles per scene. They end up being fairly good at the depth complexity, too. So this is like a really complicated map, and it's got lots of layers, but you can look here and compare the number of fragments to the size of the image and see depth complexity here is roughly maybe 2 or a little bit more fragments for every pixel. Okay, so they need to manage that to make this work well.
GL question. So between GL begin and GL end, does that represent one object in the, like, what is that exactly?
It depends. You could make it represent part of one object. You could make it represent many objects. You could make it represent one object. It's just a question of how you structure it. Okay. I did want to have just a couple points here on this triangle size and depth complexity because this is important. We're interested in the average size, and you'll find this out when you work on your second assignment. You're interested in the average size per frame of how big triangles are. Okay? And we can measure that. We can say that the average area is equal to the number of fragments we draw divided by the number of triangles that we draw. Okay? This average area is really important. If you build a graphics processor that looks like the graphics pipeline, okay, so has different pieces of hardware for each stage in the pipeline, then what this triangle area sort of represents is this balance between the vertex part of the pipeline and the rasterization part of the pipeline. Okay? So if you decide, I'm going to put a lot more floating point computation in my vertex part, okay, then you have the capability of handling more triangles per fragment. So if you want to keep all the parts busy, the average triangle size will go down. Okay? If you decide to put some more resources in the fragment part, okay, then your fragment part can handle more and more fragments, so your average triangle size should go up. So it's this balance between the two. And so if you look at a graphics card and you say, okay, how many fragments per second is it built for, and how many vertices per second is it built for, you could say that maybe the designers said at design time, this is how big our triangle should be. Okay, and I've got some statistics on this that I'm not going to talk about in this talk. But if you build an application where your triangles are bigger than that design point, okay, then it's likely you're going to be fragment limited. And if you build them with triangles that are smaller, then it's going to be geometry limited. Okay, we're going to talk about this more. This is really what you're going to explore in assignment 2. Sort of this trade-off between geometry performance and fragment performance. And we'll talk about that throughout the class because it's really sort of one of the important parts about graphics hardware. Just wanted to look at like some different characteristics of these scenes in terms of triangle size. So what we're going to look at is 3 scenes here, and you see these 3 scenes are in very different shapes. Okay? So what we're looking at here is how many triangles we have for every triangle size. And this says that most of the triangles, and in fact most of the pixels, are concentrated in very small triangles. Okay, so these are small triangles. These are larger triangles, and you see that most of the triangles are sort of medium-sized here. But obviously the big triangles have more fragments, so the bigger triangles take up most of the fragments. And then when you look at a scene that actually does have really, really big triangles, then there's more big triangles and they take up way more of the fragments. And so it's a real challenge to build a GPU that works well on all these things. Because at design time, you have to figure out what resources am I going to put toward my geometry and what resources am I going to put toward my fragment.
So for this picture, you said it was a cylinder made of triangles. So
big triangles.
So shouldn't they all be the same exact size, all the triangles?
Well, it depends on the projection, right? Depends entirely on the projection. You can project a giant triangle, really close to you or far away or in the corner or something. It'll depend on the projection. Okay. So they're all the same size in world space. They're not necessarily the same size in screen space. Okay, so we look historically at how this goes. Okay? These are SGI machines. How many triangles could it do per second versus how many fragments could it render per second? Okay? How big is the average triangle? Okay? So first, you could only do really, really big triangles and keep your machine busy. As time went on, the size of a triangle that would keep the machine balanced between fragment work and geometry work got smaller. Okay? And you know that because your games, over time, triangles have got smaller. Models have been more detailed. We put more resources toward fragment processing, and thus we could have smaller triangles. Okay? So we went from huge number of pixels per triangle down to a reasonable number of pixels per triangle. Okay. So you would expect this trend would continue, but if we look at Nvidia's over a decade, okay, this is really interesting. Okay, look at the right column there. How has that changed over time? Okay, so Nvidia found what they think is the sweet spot as far as how big triangles should be. And Nvidia is saying triangles ought to be somewhere around 8 pixels per triangle. That's the balance point on our architecture. Okay, I stopped when I did for a reason, and it's because they've changed the way that they've actually built the GPUs at that point. We'll talk about that in a lot of detail as well. But it's a real difference from what we see here, where it's changing from generation to generation, to here, where it's pretty much flat. Cool?
Looks like if you go to the previous chart, so it went down, and that's in 96. It got to 83, and then if you go to the next chart, it keeps going down from 83 down to roughly 10, and then it kind of stays there. And this is 97.
Well, no, I mean,
right?
It's 83 here and immediately goes to 6.
Yeah.
So it's an order of magnitude.
It's a big jump down, but.
Okay, but it's constant.
And beyond that, it stays constant.
It's pretty much constant for a decade. I mean, it doesn't vary more than a factor of about 2. And it's around the same average. Okay, so difference in the way that they've thought about doing things. In general, yeah, we're going to skip all this because I want to get to the project kind of thing. Come back and do this. Okay, so we talk a little bit about the assignment. So this is on the website now. You got 3 weeks to do it. What I'm interested in seeing you do is exploring crossover point between geometry and rasterization. Okay, so I want you to vary triangle size and tell me how many fragments per second I'm rendering and how many vertices per second I'm rendering. Okay? With really big triangles, you're going to get a really high fragment per second number, but a pretty small vertex per second number. With really small triangles, you're going to get lots of vertices per second, but not very many fragments per second. I want you to characterize that for your graphics card. If any of you have graphics cards that don't work for this, then I'm happy to lend you one from our stash. Okay? And I'd like you to look at this for different kinds of triangles. Because these different kinds of triangles have more or less work for vertex stage or fragment stage. Right? If we're doing shaded triangles or textured triangles, that's adding more work per fragment stage. Okay? Lighting triangles adds more work for the geometry stage, and so on. So your goal is that Graphics Bench will help you do this. And you don't have to change a lot of code in Graphics Bench, but you can download this from the website. And by the end of this week, to have that running. That's your goal. Better if you can have this test done sort of by next week, and you can move on to the next part of the assignment. Okay, so this is sort of the first part of the assignment. Okay, so there's a couple ways you can go from here. And one is to do further explorations in terms of graphics performance. The other way is to look at the general purpose capabilities of your GPU. All right, so one thing you can do in the graphics stuff is you can do more in-depth study of an aspect of performance and see how that varies. So for instance, the rasterization study, maybe what we're going to change is the shape of the triangles. Okay? We're going to change from like short squat triangles to triangles that are kind of squarish to really tall skinny triangles. Does that affect the rasterization performance? Okay? How does texturing, okay, if you do one texture per fragment versus 10 textures per fragment, how does that affect this sort of curve? Okay? What's the impact of programmability? What if we do vertex engine versus hardwired calls and so on? So these are also described. But I'd like you to look into more detail into one aspect of graphics performance and this sort of curve, this characterization of triangle size versus performance. Okay? And then what I'd like you to do is look into an undocumented feature. So we have a huge list of undocumented features that the vendors don't tell us what's happening there. And I want you to run an experiment that's going to help you derive one of these. So let me just sort of talk about one of them. And this turns out to be very hard. So this is a big challenge if people want to do it. How big are the texture caches in a GPU? All right, so what you could think about doing is rendering a whole bunch of scenes, and each scene has a little bit more texture that it uses. Okay, so you start with a little tiny bit of texture, and then you have more and more texture with every scene. And at some point, maybe you blow out the cache, and your performance should crater, because suddenly it's going to memory instead of cache. Okay, so that makes a lot of sense. It turns out it's very complicated. And people have tried this in the past, and it's a hard thing to do. People have been successful, but it's difficult. Lots of different things that we have a big list of things. I'm happy to listen to things that you're interested in. But your goal is to convince the graphics hardware to tell you something that the vendors aren't going to tell you. You're going to write experiments, design experiments to do this. And I'm happy to hear your ideas on how you do this, offer some suggestions on how you do this. But your job, from the graphics point of view, is to do this. Okay? This is one that's been popular, sampling locations. Right? You have sort of you have a pixel. It's not really a little square, but for the purposes of this, I'll say it's a little square. All right? Where do we take the sample? Is it in the middle? Is it over here? There's lots of schemes where we take multiple samples per pixel. Where are those? Okay? So your job is to come up with a way to figure that out. So lots of ideas here. If you're doing the GPU side, it's sort of specific to G80 class hardware, although if you want to use an AMD one, that's fine. I'm happy to lend you a card that'll work here. But for you to characterize the compute performance on sort of 4 different axes, and again, this is described on the page, but this is where you have to write a particular set of experiments to do these things, to characterize the performance of the GPU in these different aspects. Okay? So you got 3 weeks to do these. Everybody's going to do this first one here. So this is a good thing to start in the first week, and then maybe you spend a week on this guy and a week on the next guy. So happy if you do any of these. Again, email me if you've got any questions. What I'm going to want is a PDF write-up when you're all done. I urge you to try to make them succinct and turn in your source code, and you'll turn that all through SmartSight. So your goal is to learn something. So that's what I really want to see out of this.
Okay, so question. If we're in graphics land,
okay.
We know how many vertices we're generating, but how do we obtain the number of fragments generated by rasterization?
Okay, so you are going to have some. You are going to design the program. Okay, the program is going to say fill the screen. You know how many fragments there are on the screen. You know how many triangles you drew. You can thus derive what the triangle size is going to be. Okay, you get to define your transformation matrices, so you're going to know how many fragments you draw.
Okay.
All right, see you guys on Thursday.
I can ask you.